Hey everyone, I'm Nick from Coffee Before Arch, and in this episode of C++ Crash Course, we're going to be talking about optimizing applications. And we're going to start this little mini-series talking about, how do we even go about this process when we're, just starting out, right? So something a little bit more real, like we don't know anything about the application ahead of time, and we're not going to assume anything about the application. And so we'll start with something that's very common operation, which is matrix vector multiplication, right? This is something that's very, very common. There's dense versions, which we're going to be looking at today. Sparse versions are run a lot, and a lot of these types of operations are even generally accelerated on things like GPUs, but we'll use it as kind of a springboard to introduce some topics. So let's go ahead and take a look at the code, which is just in this mvbench.cpp. So we go up here, and our matrix vector code is extraordinarily simple because a naive version of this is going to be very simple. All it does is it goes over, every single row in a matrix, multiplies that matrix by the same vector, right? Multiplies each element, and then sums all of those products together, and then stores it in this result over here. Right? Very simple. And so all we'll do here is we'll allocate some space, and then what we're actually going to profile is matrix vector multiplication. And then at the very end we'll print out some things, how many things we processed, as well as the number of bytes we processed. And then we'll go ahead and do this for a set of inputs, right? So we'll do it for so this is going to be a power, right? So this is going to be 2 to the 8 all the way to 2 to the 10, right? So we'll have a 256 by 256 matrix, then 512 by 512, and then a 1024 by 1024 matrix, right? So we'll see it across, kind of a range of inputs. So let's go ahead and just compile this and see what happens, right? So we'll do G++, mvbench, right? And then we'll also add, I don't think I need the C++ 17 standards. We can go ahead and take this out. I don't think I used anything from there. But we'll compile with, libbenchmark, pthread, because that's what's required by Google Benchmark. And we'll even add this -m avx2 just to make sure that, we're going to have some vectorization in there potentially. So we'll compile this, right? And there's our mvbench, and we can go ahead and run it. Right, so, right off the bat, we don't really have any intuition to what's going on here. We don't know, is this a good performance? Is this a bad performance? So what do we do now? Since we have no other reference point, a good question to ask is this application compute bound, or is this application memory bound? If we have a memory bound application, that means we're going to be really stressing the memory system. It'll be close to if we were only doing something like reads or writes, or a combination of reads and writes. If we're compute bound, that means we're trying to process, more data than can actually be processed at any given moment, right? So we're not going to care as much about, the memory bandwidth. That's not actually our concern in those cases, because we're mainly just churning and working on data. So let's try to answer that question first. And an easy way to do this, like we've seen in so many other videos so far, or in the past couple of videos, right? This has come up a lot. We can just use perf, right? So perf is a great tool for figuring out something like this. So what we'll keep track of is this bytes processed per second. And one thing we can just kind of do off the bat to figure this out is by doing something like perf record, right? So this will give us a profile of our application, right? So we'll run it, and then we will get a report that gets generated, and then we can open up that report using perf report, right? So here we are. We see most of our time, of course, is going to be spent inside of the benchmark itself, and we go in here, annotate, and here's our kind of inner loop here where we're actually doing matrix vector multiplication, right? And we already see that there are some optimizations in here. We have some vectorized instructions, as with these vMoveSS, vMulSS, vAddSS, right? So we made sure to give it a fighting chance, just looking at our naive code to do something. And what's going on here? So based upon what perf is telling us, right? So 69% of our time and 27% of our time, respectively, is being spent on this vadd and this vmul. So by the looks of it, it looks like we're compute bound, but we don't want to be too hasty. Perf, of course, isn't perfect, right? So whenever we're collecting performance counter information, it may attribute it may attribute those samples to maybe the instruction before or the instruction after. So we have to be, kind of careful in terms of, just believing, at face value what's going on here. So sometimes we want to, dig in a little bit deeper. Sometimes it's obvious, sometimes it's not. So just to make sure that it's not, say, a move instruction where we're loading from memory, we can go ahead and just see, well, if I'm only doing something like loads, right? So we'll just look at something like the actual loads. We should get similar, maybe less, maybe more performance from something like stores, but we'll have another benchmark, right? We'll call this ReadBench. Now, this isn't going to be a very optimized benchmark, but this is just, to get the point across to see what's going to happen. So we'll go ahead and just load a whole bunch of, we'll initialize some random data into matrix, and then we'll go ahead and just load it into a variable we call sync, right? So it's just going to be a sync for all of our loads. We're not doing any compute in this loop. All we're doing is going to, read out whatever matrix, whatever values in that position matrix. Right, so let's see what we get here. Right, so we can do same thing, G++, right, and we can have ReadBench. We'll link against lib benchmark. Oops. There we go. And now pthread, and then O3. We can even, maybe x2, and then we can have, what our output is. We'll just call it something like ReadBench. All right, and then let's run ReadBench. Actually, let's get MVBench back on the screen. That way we at least have those performance numbers to compare against, right? At least in terms of, the read and write combined throughput there, right? All right, so let's go ahead and run ReadBench this time. And what happens? Well, that's a very different number than what we were seeing earlier, right? So, our suspicions were correct looking at the actual instructions. We really aren't memory bound in this case, right? So we're reading from, memory, but that's not what's taking the most time. It turns out a lot of our time is being spent on the compute, right? So, we could theoretically have a lot higher, or a higher rate of reads than we're actually doing. So we're compute bound, and we can even kind of show this. So if we, open up, if we do say perf record on our ReadBench this time, right, we can even see what the profile of what's going on there, right? So and then let's do perf report, and then here's most of our time is being in ReadBench. Where in ReadBench? A vmove instruction, right? So clearly it's going to be, inside of some kind of move, right? All right, so that's going to be the basics of the start of this series. So one of the things we always want to do whenever we're starting out in optimization, we have to diagnose, where do we have room to improve? Are we capped at memory bandwidth? Are we capped at compute? Or are we someplace in the middle? So next time we'll look at trying to solve this problem. Specifically, we'll try to solve this problem using SIMD or vectorized instructions, right, and vectorized loads, and vectorized, multiplication operations. See if that'll fix it. So, like I said, that's going to do it for this time. Feel free to check out any of this code at github.com/coffeebeforearch. So this is going to be under C++ Crash Course, Optimization, and then under Matrix Vector, right? So we've got, this benchmark in here, so feel free to download it, play around with it. Let me know if you have any questions. As always, hope you have a nice day.